Through our study of the difference amplifier, we've seen that the output voltage Vout is equal to R2 over R1 times the difference of the two input voltages. We've also seen that any common mode noise that is present on both of the leads to the amplifier, is removed by the differencing operation. But we've also seen that the difference amplifier has a relatively small input resistance. In this video, we'll show how the difference amplifier can be modified to address this weakness. This enhanced difference amplifier is known as an instrumentation amplifier. To address the problem of the small input resistance, we add a voltage follower or buffer preamp stage to both inputs of the difference amplifier. As we know, the input resistance for a buffering amplifier is just the input resistance seen looking into the non-inverting terminals. In the ideal op-amp model, this resistance is taken to be infinite. The buffers also have a small output resistance and provide some current gain to drive the difference amplifier. These buffers address the limitations of the difference amplifier very nicely. But if you think about it for a while, you might realize that if we're going to the expense of adding 2 additional op-amps, why not get some gain out of them also? Replacing the buffers with non-inverting amplifiers does just that. We still have the infinite input resistance going into the non-inverting terminals on both sides. And we have the current gain, but now we also achieve some voltage gain. Both of the voltages, Vi1 and Vi2, have been amplified by the non-inverting amplifier gain. Now let's take just a moment to point out the resistor names. Here we're using the resistors R2 and R1 in both of these amplifiers to serve as the feedback resistor and the resistance going to ground. So at the output of this first stage, both Vi1 and Vi2 have been amplified by the gain 1 plus R2 over R1. Now over here in the difference amplifier, we're using resistors R3 and R4 to provide the gain and the differencing function in the differensing amplifier. So just be aware as we go on here that R3 and R4 are in the differencing stage and R2 and R1 are in the preamp stage. Now there's a challenge with this circuit. Because the op-amps won't be exactly ideal, and because of variations in resistor values, it's likely that some tweaking will be necessary in practice to realize the same gain in both non-inverting amplifiers. As is shown in this circuit here, we have 2 feedback currents. We have the feedback in this amplifier going to ground, and we have the feedback current in this amplifier going to ground. In practice, balancing these 2 separate or independent amplifiers can be challenging. And further, over time, performance tends to drift a little, causing further imbalance in the amplifiers. So to address that, we remove this ground at point X, which then places all 4 of these resistors in the same feedback path. We have 2 R2s and 2 R1 resistors now in series. We show that over here in figure B. Coming from this output, going through R2 to the inverting terminal of this op-amp. That current then continues on through a resistor that we're marking as with the value 2 times R1, and then back on up through R2 to the output of this amplifier. Again, this combines the feedback paths of the 2 non-inverting amplifiers, and it allows us to balance the gains with a single adjustment, typically using a variable resistor here. And we can calculate the feedback current that is going through this path. Realizing the virtual short across here, that makes the voltage here to be Vi2, and again the virtual short here makes the voltage at this point Vi1. So the voltage across this resistor is just Vi2 minus Vi VI1. And that feedback current then, if we call that difference VI2 minus VI1, if we call that VID, V sub ID, then the current in the feedback loop is just VID divided by 2 times R1. And down here in this final schematic here, we then see the different values in the circuit. We've got the feedback current VID over 2R1, the same current in both feedback loops. At the output then of the first stage, we have this VID again, which is just VI2 minus VI1, so times the non-inverting op-amp gain, which is 1 plus, note there's 2 R2s in the circuit, and this value here is 2R1. So we have then the amplifier gain of the first stage is 1 plus 2 times R2 over 2 times R1. Of course, the 2's cancel. So we still have that same gain, 1 plus R2 over R1, as at the input to the difference amplifier. The difference amplifier then multiplies that difference by the gain R4 over R3, so that we get then the final output voltage is equal to the differential voltage V1 minus V2 minus V1 times the gain of the non-inverting preamp times the gain of the difference amplifier. And we can then write the overall gain for the instrumentation amplifier, call it A sub V overall, is equal to R4 over R3 times 1 plus R2 over R1.